Yeah,
think
yeah.
you can do it too. You know, I'm much more jumpy typically.
Right.
You are more calm.
But with these things, like it's such a tiny mic, even if you move your mouth a little bit, people can't hear anything. perceptron struck back. You can call it perceptron plus, namely SVMs. And they were extremely influential, and they wrote on convex optimization theory, generalization theory, expressivity theory of kernels, etc. So there was a lot of theory there. But of course, in the last 10 years, it's been the age of deep learning, which you can think of as multi-layer perceptron. And somehow people got over this issue that with deep learning, you won't have a provable solution, any guarantee that you're at the optimum solution, and you just go, live with it. So in this talk, we'll look at what's the theory one can do here. And many people originally seem to assume, including back in the 50s, that this is a no-go zone because of various complications. But we'll actually see that there's interesting theory to be done. I'll start by telling you some terminology just so that we have a common notation in our discussion. So theta denotes the parameters of the deep net. And there's training data, which is sequence of data points, xi's, and they label yi. And these are supposed to be IID draws from some distribution of all possible training data. And so this is your training data, the sample. And the loss function, given an input x, a data point x, and a label y, is some function, for instance, L2 or cross entropy loss, which describes how well this net theta on input x, the output that it produced, matches y. Now, the objective is to minimize over theta this training loss. And I'm writing it as expectation over training points, E sub I. I is the index of the training point. And that expectation is just the sum, or the average. And in practice, you just try to train it using gradient descent, the most simple algorithm in continuous optimization, and which is like this, where you compute the gradient of this loss and go in the direction of negative gradient times an eta, which is called the learning rate. And stochastic gradient descent is the same algorithm, except because computing the gradient can be very expensive when you have millions of data points, you estimate it via a small sample of training data. I'm assuming this is all known to you, but just wanted to lay down the notation. So the point I want to make is that optimization concepts have already shaped deep learning a lot. Together with, of course, things like GPUs and large data sets. So for instance, backpropagation, a very old algorithm, goes back in the main ideas to the 50s or 60s. And in the modern incarnation, it's very important because it's a linear time algorithm. Linear in the size of the network. And that's very important because networks today have millions of parameters. So a quadratic time algorithm, which would be naive, would be too expensive. So backpropagation is great that way. Then gradient and landscape shaping have driven innovations in deep learning in recent years, such as ResNets, WaveNets, batch normalization, etc. And these are also related to optimization. And arguably, this is the stuff that didn't exist so much 20, 30 years ago. And this is driven by innovations in modern optimization theory. Then there's a bunch of techniques which are called gradient descent plus plus. So instead of using just vanilla gradient descent, you add ideas like momentum, regularization, AdaGrad, etc. And these also came from convex optimization world. So I won't talk about these today in detail at all, but I wanted to put this up there, that this came from optimization as well. So goal of theory is theorems that sort through and support such these competing intuitions that you often have in deep learning, and you hope that they lead to new insights and concepts. But yeah, this what theorems is highlighted in red because that's really important, a mathematical basis for various intuitions and ideas. And in today's talk, I'll be largely talking about things that have happened in the last few years, so not classic convex optimization and so on. And here's a talk overview. The first part will be optimization. When and how can this training find decent solutions? Because the landscape is highly non-convex. It has these hills and valleys. And if you start at two very nearby points, the path you take via gradient descent may land you in very different places. So that's a property of non-convex landscapes. The next part will be some consideration of overparameterization and generalization. So in neural nets today, very often, the number of parameters, training parameters, is way more than the number of training samples. So does this help, and why? And secondly, why do these nets generalize? That is, predict well on unseen data. Because classic statistics tells us that these kinds of nets with so many parameters, more than the number of training samples, can overfit. And actually, it doesn't seem to happen. So that's an active area right now to understand that. The third part will be the role of depth. Why depth in deep learning? The next part would be unsupervised learning and GANs. There's been, in the last couple of years, some theory about that. And finally, some examples of simpler methods to replace deep learning. This is not necessarily a suggestion that deep learning is going to be all replaced by simpler methods, but at least when you try to think about simpler, understandable methods, maybe you'll be able to learn from them and improve other methods. So the methods I'll talk about are actually linear in some sense, although not in the obvious way. So let's start with optimization, part one. So as I indicated, the hurdle in developing the theory of optimization for deep learning is that most of these optimization problems, even simple subcases, are non-convex. And if you are interested in computational intractability, then, well, on worst-case instances, most of these problems are NP hard or something like that, some such hardness notion. And so you don't expect to have a provably polynomial time algorithm for these problems, at least on worst-case instances. So how do you proceed with that? So some basic concepts in discussing optimization. So by definition, if the gradient is non-zero, then there exists a descent direction, right? Because that's the definition of gradient, or that's the meaning of the gradient, that if you make an infinitesimal change in the parameters, then gradient tells you the direction of maximum change. So if the gradient is non-zero, then the negative of the gradient is the direction in which the loss is going to decrease. So possible goals of algorithms. You could find just a critical point, okay, where the gradient is zero. So at least in that point, there's no local improvement of the loss function. The next more stronger notion would be to find a local optimum. That is the bottom of some valley. In that picture, the bottom of some valley. It need not be the global optimum, but it could be a local optimum. Mathematically, a local optimum can be defined in many ways, but the one we are interested in is that the second derivative, the Hessian, is positive semi-definite. That's saying geometrically exactly that it's the bottom of a valley. And then the most ambitious goal would be to find the global optimum. Assumptions about initialization. Well, you're going to start off the optimization from some point. So what is that initial point, and what's your theorem going to say? So you could try to prove convergence from all starting points. That's the most ambitious. You can prove convergence from random initial points, and that's, of course, the most common form of initialization used in deep learning, small random initialization. Or to make life easier for theory, as a first step, you could try to prove initialization from some special initial points. And you could then describe how to get to those initial points in some way, and then from there, gradient descent could take over. Another crucial concept to be aware of is black box versus non-black box analyses, which I'll talk about more in the next slide. An important point to make is that in theory, we are interested in efficient algorithms, provably efficient algorithms. And if you have D parameters, so your optimization is in RD, then you want running times of polynomial in D and 1 over epsilon, where epsilon is accuracy. So that's just tradition in optimization theory to express running times like that. Obviously, you want polynomials that are low, like linear or something like that. The important point to note is that the naive upper bound would be exponential in d over epsilon. And let me explain that. So there's a simple fact about high-dimensional geometry, which is not always known. And I remember when I first learned about it, I was quite surprised. So it's this fact that there's a lot of distinct directions in d dimensions. So in d dimensions, there are exponential in d directions whose pairwise angle is at least 60 degrees. So I've illustrated that using this sea urchin figure, this spiny figure. Now, a sea urchin is in 3 dimensions, and it has a lot of spines, so those spines are packed together a lot, right? They're very tied together. But in d dimensions, you could have this similar kind of sea urchin, maybe you can call it a d urchin, where there are lots of spines, exponential in these spines, but each of them makes an angle 60 degrees with each other. So there's just a lot of space in high dimensions. And so there's a lot of space, but there's not too much more. So there are also exponential in d over epsilon special directions, such that all other directions have angle at most epsilon with one of these special directions. So this is called sometimes an epsilon net or epsilon cover. And so this is where the exponential in d over epsilon comes from. So if you were just walking around in d-dimensional space and just walk around until you hit a good solution, well, the time to explode in a d-dimensional parameter space would be like this. And that's, of course, infeasible for any even modest d, let alone d being a million. OK, so by the way, this sea urchin figure I'll put up whenever I use this fact about d dimensions. So going back to black box versus non-black box. So why black box analysis for deep learning? And the answer is that we don't really know the landscape. Now you might say, wait, don't know the landscape? You just put up the loss function in front of us, right? This one. There's nothing unknown there. You're given the training data and the labels, and there's a simple loss function, L2 or whatever, and then you're summing over data points. The loss function is written down before you, right? OK, it has 1 million terms, but fine. For a computer, it's fine. So what's unknown about it? And the answer is that there's no clean mathematical characterization of these data points. What makes a sequence of pixels, an image of a dog or a cat? There's no mathematical description of it. So as far as we're concerned, there's this million-term objective, and it has all these terms in it which we have no mathematical understanding of. OK, so as far as math is concerned, we might as well be dealing with a black box. OK, so for a full deep net with many layers and so on, that's really the only kind of analysis we know. And so what is this black box, and what do we know about it? Well, we can evaluate this black box, meaning this training error, at any point. So you take any theta, and you can evaluate it, you being the computer. Obviously, it has 1 million terms. So it can be done efficiently. And you can evaluate the gradient. Those are both efficient operations. So that's a black box. You feed it theta, and you can get the value or the gradient. And notice that given just such a black box, it's infeasible to find a global optimum. Because it could be that in this black box is representing a function which is basically the same everywhere. And then there's this one direction in d dimensions where it suddenly plunges to some low value. So now any black box algorithm will have to explore all of d-dimensional space to find this one direction where it's low. OK, so in a black box model, you cannot have a feasible solution to find the global optimum. So you have to settle for one of the weaker concepts, and that's what we'll see how you can do. So in an unknown landscape, gradient descent is going as follows. OK, if gradient is not 0, then there's a descent direction. However, that's not quite right, because suppose you move along the negative gradient for a little distance. If the second derivative is high, what does that mean? It means second derivative is the rate of change of the first derivative. So if the second derivative is high, it allows the gradient to fluctuate a lot. So now if you move a little bit in the direction of negative gradient, suddenly you might find, oh, it's changed. So actually you didn't actually descend. You didn't decrease the loss function. So we have to assume that the second derivative is not too high. So to ensure descent, you have to take small steps, and that are determined by the smoothness. Okay, so there's some bound on the second derivative. This is just saying that this second derivative matrix. So the second derivative, if there are d variables, is a d by d matrix, which is a partial derivative with respect to xi, xj. So this is a matrix. The second matrix is called the Hessian, and it has some bound on its eigenvalues. It's not going to be important, this bound. So there's some bound on the second derivative. And by the way, this bound can be assumed via some Gaussian smoothing of f, although we don't normally do that. But if you wanted to, you could do some Gaussian smoothing. OK, so now there's a bound on the second derivative. What happens? So the claim is that if you make small enough steps, so this learning rate is less than 1 over 2 beta, then you achieve you make the gradient norm smaller than epsilon in number of steps proportional to beta over epsilon square. So beta is this bound on the second derivative, and epsilon is how small we want the gradient to get. And this is possibly the only proof I'll do, because it's a two-line proof. So from the meaning of smoothness, turns out, if you think about also the one-dimensional analog, is that if the second derivative has a bound of beta, then what that means is that the first-order approximation to the function is basically correct up to this quadratic term, beta times the quadratic term. So then the difference between two successive steps is given by the gradient times the displacement, plus this correction term, which is quadratic. And so now, since you moved by an amount eta times the gradient, the first term is eta times the norm of the gradient square, and the second one is like beta times eta squared times the norm of the gradient square, which is like 1 over 2 beta times eta square. Sorry, the gradient square. So what this means is that so long as the gradient is large, you're making progress. So this update is reducing the function value by epsilon square divided by 2 beta. Okay? And so at every step, you're making this amount of progress. So the number of steps you need to get down to, say, to zero gradient is at most the reciprocal of this, which is like beta over epsilon square. Okay, that's essentially the only proof. I mean, all I'll do are these two-line proofs. So that shows you that you can get to a critical point, okay, or close to a critical point. But that's actually a weak solution concept. And the reason is that high-dimensional geometry is more complex. And you can have things like saddle points, where the derivative is 0, but it's actually not a minimum in any sense. So for example, you could have, as the name suggests, this saddle shape, where you had a point where it's a minimum in n minus 1 dimensions and maximum in the other. So that's a saddle point. You're not really at a minimum. There is actually a direction where you can improve the function a little bit. But it's very hard to find that in d dimensions. So a very nice paper by Ge, Huang, Jin, and Yang showed that actually you don't need to worry about saddle points, provided you're willing to add noise to the gradient. So this is the so-called perturbed gradient descent. Now, am I saying that you should be adding noise to your gradient descent? No. The suggestion is just that, in stochastic gradient descent, there's all kinds of sources of noise from the sampling or from the data points themselves. So it's believed that actual training and deep learning already has a lot of sources of noise in it, so you don't need to add noise. But for analysis, you imagine that noise has been added to the gradient. And now, the gradient descent, which was a deterministic algorithm, right? You're following just the gradient at every step, becomes a random walk. Because at the next step, where you go is somewhat noisy. So it's a random walk in d-dimensional space. And you have to analyze this random walks, which is what these people do. And they show that within polynomial in d over epsilon time, you can escape all saddle points and achieve what's called this approximate second order minimum, namely where the norm of the gradient is less than epsilon. And the second derivative, the Hessian, is not quite positive semi-definite, which is what you need for the bottom of the valley, but it's almost positive semi-definite. So that's where you reach. So that's a very nice result. So it's a somewhat stronger solution concept than just critical point. Okay, so talking about second order methods and second order notions, what about second order optimization for deep learning? So because in classical optimization, it's actually quite normal to use the second order derivative, the so-called Newton method. So which, remember, looks something like this, that your update is not just along the gradient, but it's actually scaled by the inverse of the Hessian. Now, remember, we're in the black box model, right? So all we have is the value and the gradient. So we can't even, so far in the black box model, we don't even have the Hessian. Turns out, even back in 1974, Verbos showed that backpropagation can also compute the second derivative quite efficiently. So actually, in this black box, you can add the second derivative as well. And actually more relevant for this, since we're interested in linear time computations because deep nets are so large, turns out Perlmutter showed in 94 that for any vector v, backpropping can compute this matrix, the Hessian times the vector, this matrix vector product, in linear time. So that's a very nice result, and that's going to be useful here. But it seems relevant, but actually if you look at it, the Newton method needs the inverse of the Hessian, the inverse matrix. Now, matrix inverse is no joke either, right, optimization-wise. So this doesn't quite get us there. But nevertheless, these papers have shown that you can do approximate second-order optimization, which is asymptotically faster than the first-order method that we saw in the previous slide, using the noisy gradient descent. And the idea is that you can approximate this inverse of the Hessian, the inverse of the second-order derivatives, by this infinite Taylor series, which is identity minus the Hessian square to the power I, the sum over that. So that's a simple identity. I mean, if you just put x in there, you'll see that it's true. And you use the finite truncation of that series. And so on the right-hand side, now you have these Hessians, obviously with higher powers, but turns out you can backpropagation can be used to approximate those as well. So yeah, second order is very good. Now notice that the moment you change the algorithm in deep learning, because it's non-convex, you may find very different solutions than gradient descent may. And so you might hope that this second order method finds somehow better quality nets. It's exploiting second order information, but so far it doesn't seem to find any better nets. So it's a great idea, but so far we are still, it's probably just better to use gradient descent. Okay, so these were this was a tasting of black box analyses. And what about non-black box analyses? That's a very, very difficult problem for multi-layer deep nets. And the current state of the art is that you consider various machine learning problems that are subcases of depth 2 nets, okay? Namely one hidden layer between input and output. So it's a very simple deep net, and even of that you take a subcase, okay? So subcases are things like topic modeling, sparse coding, phase retrieval, matrix completion, matrix sensing, learning noisy OR nets, etc. So these are kind of simple cases of depth 2 neural nets. And all of these non-black box analyses have to make assumptions about the net structure, data distribution, etc., so that the landscape is mathematically understood. Okay, because if the landscape is not known, there's no hope for a non-black box analysis, as I indicated. And often they don't even use gradient descent. They might use tensor decomposition, alternating minimization, even convex optimization. Although lately there's some progress towards actually using gradient descent, as I'll discuss now. So just in the last year or so, there's a progress on actually analyzing some of these special cases of depth-2 nets via actually gradient descent. So even the analysis of gradient descent. And here's a very nice paper about matrix completion, which is a problem that theorists love, and there's been thousands of papers on it since in the last 10 years. And now there's sort of an analysis of matrix completion in the spirit of deep learning. So matrix completion, in case you haven't seen it, is the following problem: that there's an unknown matrix M, and you're given some random sample of entries in it, and you're trying to recover the rest. So it's used, for instance, it was proposed, for instance, in the context of recommendation systems. Okay, so you're given some random entries of this matrix, and you're trying to predict the missing ones, and the number of entries that you're given is very small. Now that, of course, should not be enough in general to allow you to predict the remaining entries, because you're just given some small number of entries out of n squared. But you can do something if this matrix is low rank, say of rank R, where R is pretty small. Think of it as, say, 50. So now you're given these random entries, and you're trying to predict them. And there are many algorithms for doing that, including convex optimization. And let me point out that it's a subcase of learning depth-2 nets, because you can think, in fact, depth-2 linear nets, because you can think of it as this net where, remember, M is a product of two rank R matrices, U and V. So you can think of a net where the lower layer is U and the upper layer is V. And it's just a linear net. And what's the data that you're given? The data is just, you're feeding one hot inputs into the unknown net. Oops, sorry, not seeing the output at one random output. So you're given entries ij, so that's like feeding in the input 0001, 000, where 1 is in I location, and you're reading the jth output. Okay, so that's completely equivalent. You're feeding this input, and if you think about how matrix vector product works, it's just giving you this matrix times this number, and then you're getting the jth entry, so that's just the ijth entry of the matrix. All right, so just a depth-2 neural net learning problem on some very special data, very, very specialized. Okay, and even this is pretty hard, okay, to analyze. And only last year, Gurley and Ma showed that for this problem, all local minima are global minima. Okay, and so perturbed gradient descent finds the global minimum, by the previous slides, from an arbitrary initial point. Okay, so it's even this, this is fairly non-trivial. So this is just to give you an idea of how difficult and hairy things get, even for very simple settings in deep learning. Okay, and finally, any theorems about learning multilayer nets? Yes, but usually only for linear nets. That is, the hidden nodes are not computing on nonlinearity, but just identity. And so the overall net is just a product of matrix transformations, right? Matrix, 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 which are being multiplied. Just the d-dimensional version of matrix completion you can think of. And so it's non-black box. Okay, now we understand this mathematically. But still, this optimization landscape holds surprises, and we'll talk about some more surprises later on. And there's been a bunch of papers, which I won't talk about. Okay, so I'm approaching the end of this optimization section. Some other optimization ideas I did not cover, and many of them currently are really in the semi-theorem form right now. So there are budding connections with physics ideas, natural gradient, Lagrangian method. There's some budding theory to understand adversarial examples for classification problems and efforts to combat them. There's some optimization ideas for unsupervised learning, especially probabilistic models, reinforcement learning, etc. There's very nice connections to information theory, things like information bottleneck. But again, as far as I can tell, mostly semi-theorems, and I'm not an expert on those anyway, so I won't talk about them today. So that's the end of first part, and I'll go on to, that was the longest part actually, and now I'll go on to talking about overparameterization and generalization theory. So as I mentioned, and as probably most of you know, these days it's quite traditional to not bat an eyelid at training a net with 20 million parameters on CFAR10 with 50,000 examples. And no overfitting is observed, or very little. So why? Okay, and why is this a good idea? So obviously, the reason people are using it is that overparameterization seems to help optimization. And let me describe that help by a very striking example. Okay, and this is a folklore experiment that probably many deep learning people have done. And I know about it from a paper of Livni et al. It's the following. Okay, it's a very simple experiment. So suppose you generate label data by just feeding data into a neural net that you know. So you have a depth 2 neural net, and you're feeding random inputs in it and outcome random outputs. Okay, and now that's your training set. Okay, so there's this neural net in your computer, you know it completely, let's say even a random neural net, random weights, and now you're feeding data and just getting the training data that way, those input-output relationships. So now you try to do the following. So you know that there's this deep net that explains the data that you've got, okay? But now you put aside that deep net and try to train a new deep net, same architecture, using that data. And now what you find is that it's quite difficult to train a new net using this label data if this number of hidden nodes is exactly the same as what was in your ground truth deep net. Okay, it's just a very hard optimization problem. But if you increase the number of hidden nodes, so if the true number of hidden nodes was 100 and you allow it to be 300, it becomes much easier. Okay, and then the optimization works very well. It's a very striking experiment. And you would imagine that this should be something that we could prove, actually. But as far as I know, there's still no theorem explaining this. And I've had a sequence of smart students to whom I mentioned this problem, and nobody has really made progress on it. I mean, there's some progress, but nobody has been able to prove it. I mean, you can even make any assumptions that you like, that the data was just Gaussian vectors that you're feeding into this net. Maybe even the net has random weights, and still, it's very hard to prove this. Okay, so overparameterization seems to help optimization. But on the other hand, fine, it helps optimization, but textbooks have warned us for decades that large models can overfit. And this is a textbook picture that this is a model complexity. Think of it as the number of parameters. And as you increase the model size, it's easier to fit the training data, so you have lower error. But then if you look at test data, at some point, the error starts going up, the U-shaped curve. And so the textbook says that the model size that you should use is at this inflection point, and the gap between the two curves is the generalization error. All right? But in real-life deep learning, often the curve is more like this. Okay, maybe it's not flat, maybe it rises a little bit, or whatever, but you certainly don't see the sharp U-curve in many settings. Now, people have known this for a long time, and the belief was that somehow all the things you're using, all the knobs you can turn in deep learning, SGD, learning rates, et cetera, regularization, momentum, blah, 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 it eliminates the excess capacity of the net, whatever that means. Okay, but there was a striking experiment last year reported in this paper by Zhang et al., which shows that the excess capacity is actually still there. So it was a very neat experiment. Probably, I don't know if anybody else had done it before that, but they did it very exhaustively. So what this experiment is, it's taking an Inception V3 net, which is a fairly large net on CFAR10. And what they tried to do was, okay, so this curve over here is just a true training curve. So, pretty soon the training error goes down to 0, actually. Okay, you're using pretty large nets. Then they start messing with the data. Okay, they change the labels randomly. They even substitute the pixels with random pixels, et cetera, et cetera. Okay, so they corrupt the data more and more. And you can do more and more severe corruptions, and the net fits them all. Training error goes to 0. Okay, and it's not even that many more steps, okay? And this shows, factor 3, factor 4, number of steps, even factor 2. And the net fits even the corrupted data. Severely corrupted data, completely random data. So it still has the capacity in there. So this was a very striking experiment. Now, I know this paper is very well known, but I should also tell you that in the theory community, many people had a bemused expression when they saw this title. Okay, the experiment is cool because it's actually the excess capacity phenomenon exists in linear models as well, and this is long known. So exactly the same phenomenon. So it's known that most of the linear classification tasks that you are interested in, the linear classifier has a margin. So let's say the margin is gamma, separating the positive and the negative examples. And this is what's called a strict margin. I won't talk about the soft margin notions. Okay, if gamma is a margin and say the data is all normalized, and the classifier has d parameters, d dimensions, then if the margin is gamma, then turns out the effective capacity, which I'll explain more rigorously in a slide or two, turns out is log d over gamma square. Okay, so if gamma is modest, the capacity scaling as the logarithm of the number of parameters, the number of dimensions. But of course, as a linear classifier, you give me d minus 1 points, randomly labeled data points, and I can still fit a linear classifier there in d dimensions. That's just because the dimension is so high. So it's the same phenomenon, okay, that's known for linear models. So it's not that, so that's why there was this paper actually, which has some more actually deeper observations. Understanding deep learning requires understanding kernel learning. It was just a tongue-in-cheek title, I believe. So, all right, so the true question raised by that experiment is not that you need to rethink generalization theory, but how do you quantify the capacity of deep nets? Okay, this was really the true message. And for a while, I thought, okay, maybe this is of somewhat academic interest because, generalization you can test by just held out data, right? And every practitioner does that anyway. So it's somewhat of academic interest, right? Whether it generalizes or not. I mean, what is a generalization bound? In practice, you can just test with held out data. But now I think actually it's very interesting because, it's probably going to give us some insight into the intrinsic structure of a well-trained net. Okay, if we understand what generalizes, then it'll give us this some insight into the structure of a well-trained net, which should be useful for all kinds of things. Interpretability, better algorithms, whatever. Okay, so this brings us to this notion of effective capacity, and this textbook picture that complicated models, instead of linear, if it's like got lots of oscillations, it requires more training data. So what is effective capacity? It's, roughly speaking, the log of the number of distinct a priori models. Okay, so before you've looked at the data, you had in your mind some set of possible models that you're trying to fit, and all possible models, the log of that is roughly the effective capacity. And this is a rough analogy that, like if you're thinking about a system with memory, if the system exhibits 2 to the k states, distinct states, we say that it has k bits of memory, right? That's just classical way of thinking about memory. So it's roughly the same concept. And the generalization theory, the main theorem, has this form that test loss minus training loss, which are both normalized to 1 in this case, the difference is at most the square root of the effective capacity divided by the number of training samples. Okay, that's sort of the goal of generalization theory. All the theorems of generalization theory have this kind of form for different types of notions of effective capacity. So there are usual upper bounds on n, such as number of parameters, BC dimension, Rademacher complexity, etc. So that's classical generalization theory. And what this paper title was really referring to was that for deep nets, all of these are about the same, okay? And they are usually vacuous. Vacuous, why? Because if these effective capacity is more than the number of training samples, or this upper bound of the effective capacity is more than the number of training samples, then this right-hand side is 1, and so this bound is vacuous. So that's the mystery. Okay, that's what this paper title was referring to, that all the measures that we know of in generalization theory lead to vacuous bounds. Okay, so this slide will also have a proof sketch. In case you've never seen this, it's worth knowing the rough idea of this argument. If you don't understand it, it's not needed for the rest of the talk. So how this kind of theorem proved? So the proof sketch is as follows. Imagine the following thought experiment. You fixed one deep net, theta, and its parameters. And now, theta is its test error, okay? The error on the full distribution of samples. So whatever it is, error sub theta. And now, having fixed the deep net, you take a sample S of m data points, and you look at the average error on those samples, which is a training error. Now, by concentration bounds, probability concentration bounds, because you took a large sample, we know that the probability that this difference between these two, the estimate of this test error on this and the true test error, the probability that difference is more than epsilon, the probability that it's less than epsilon is almost 1. So 1 minus exponential to the minus epsilon square m. That's the standard concentration bound. Now, the complication is that in this experiment, we switched the order, right? We fixed the deep net first, and then we took the samples. Now, of course, in training, you do the opposite. You first take the samples of training samples, and then you find the best deep net. So this analysis doesn't quite work, okay? Because the theta depends on the samples. And the solution, mathematically, and maybe this is not the best thing we should do, and maybe there's some smart young researcher here who will figure out a better way to do it. But the current solution is to just take a union bound over all possible theta. Okay, so now, because this probability is so small, you can take a union bound over a lot of models. And so if the number of possible models is W, okay, this script W, then it suffices to let m be more than log of that number divided by epsilon square. And you still get a probability almost 1 that the model generalizes. So all of these models generalize. Okay, so that's what the generalization theory does. It says all possible models generalize on this sample. It seems like it's proving something too strong. Okay, maybe that's a lacuna or a gap. So that's the effective capacity. Okay, as I said, if you didn't understand this proof, you won't need it except for this notion. Okay, so now there's an old notion called flat minima, which has been suggested as a reason why deep learning generalizes. And there are various intuitive arguments which say that because there's all these sources of noise in the training, for instance, stochastic gradient descent, this noise favors flat minima. So flat minimum, as the name suggests, is this region in the landscape which you can move the solution a lot in the neighborhood, and it doesn't change the value. So obviously, if there's a lot of noise in this gradient descent, it'll never find this sharp minimum, and it'll settle into some flat minimum. It'll avoid sharp minimum. Okay, so there's some empirical evidence, and including on recent architectures by Kesker et al., that flat minima do generalize better empirically. So theoretically, why should flat minima be good? And this was suggested already in the original papers, that a flat minimum has lower description length, right? No, lower number of bits needed to describe them. Why? Because, if it's a flat minimum, well, you can jiggle the solution a lot, and the value doesn't change, the loss doesn't change. And so you can imagine truncating the bits of precision, right? And so you can represent the solution with fewer number of bits. Okay, so that's an example of how, because you're in a flat minimum, you can truncate the model a bit, and there will be fewer number of possible models, okay? And that's good for generalization. So all of this makes intuitive sense, right, based on the theory I just showed you. But it's very hard to make it quantitative. Okay, and the quantitative versions you might try are actually false for some definitions, as shown in this paper of Din et al. Okay, so this was a classical notion up to like a couple years ago. And then in the last 2 years, generalization theory people have been trying to come up with better bounds. But ultimately, of course, you hope that out of this theory comes some new insight about neural nets or about training and so on. But currently, it's fair to say that what we're doing is some kind of post-mortem analysis. Okay, so, all right, so who's died? What's the post-mortem? Well, nobody died. It's the trained net, okay, that we're analyzing. And so we gather around the trained net at the end of training. And somebody says, this trained net has some property phi, whatever phi is. Could be a quantitative property. And, property phi is shared by very few nets, okay? It's a very special net. Right? So now that should be good for generalization, right? It's sort of an extension of flat minima, right? It's a property shared by very few nets. So people are trying to come up with these properties. And the first check you do is a qualitative check. Does it correlate with generalization? So I've shown you all these experiments, and there are others known, where you mess with the data, introduce corruptions, etc. And so the generalization error changes. And you check whether this property phi correlates with generalization, better generalization. So some qualitative plot like this appears in some papers, in recent papers in the last year or two. And so that's like suggestions that, okay, this property is the explanation for generalization. But now, keeping with the medical analogy, right, post-mortem and doctors and so on, well, it's just a symptom, right? The property phi is a symptom of better generalization. That's what this correlation says. It's like saying that your fever causes, some disease like malaria, right? It's the other way. Malaria causes a fever. So it correlates with generalization, but it may not be the cause. And what the cause will be is maybe a very difficult question. So in order to understand the cause, one thing you could do is a quantitative bound. So whatever this property phi is, whatever the mathematical characterization is, use that to compute a quantitative upper bound for some concrete neural net. Okay, so and so you compute this upper bound on the capacity on this very few, and that's a much harder problem. So on this plot here, you see the efforts until this year, before this conference, up to ICLR 18. So this is bounds that, so we computed for VGG 19, 19-layer neural net. So this is classic paper of Bartlett and Mendelssohn, which gives, so by the way, this is on a log scale. The true number of parameters is of the order of 10 million, so 10 to the 7, which is down here, and that's where 10 to the 44 is the height of the plot. And so if you take the naive Rademacher complexity estimate, it's like up there. And then in the last year, Neshabur et al. Came up with a better bound, which is, if you compute quantitatively for 19 layers, is something like up here, and so on. Okay, so Bartlett et al. Had somewhat better one in NIPS and ICLR. There was this other Neshabur paper, and by the way, the number of parameters is down here again. And so in this conference, we have this paper with Ge, Neshabur, and Zhang, which is a somewhat better quantitative bound, which is now roughly of the order of the number of parameters, the naive bound. And there's an asterisk in this figure, that it's ignoring things like epsilons and logs and so on. So these are only approximate computations. But at least the order of the magnitude is getting to be correct. Now, of course, what we want out of this is a capacity of 50,000, right? The training set size. Well, we don't get that. So what's the idea in this new paper? You use what we call noise stability to bound effective capacity. So what is this noise stability notion? You can think of it as a margin notion, right? So margin for linear classifier means that you can jiggle the classifier a lot and it still classifies correctly. So it's sort of a similar notion. Also, like flat minimum is a similar notion. So noise stability corresponds to studying the following thought experiment. You do noise injection in the deep net. So at some layer of the deep net, you add a Gaussian noise vector to the output x of a layer over here, let's say. So you inject Gaussian noise, and the norm of this noise is, for say, same as the norm of the vector being computed at that layer. So it's a lot of Gaussian noise. And now you inject this noise at some layer, and now you measure how the vectors computed at the higher layers have shifted. So that's the experiment. Okay, so again, you inject the Gaussian vector at some layer with a very large norm, and you measure the change in the higher layers. Okay, how much did the vector at the higher layer shifted in percentage terms? So here's the plot. So what this plot is showing is, so one is the norm of the Gaussian noise. So you injected, so this plot is for noise injected at the first layer, namely the input, sorry, the 0th layer, namely the input, first layer, second layer, etc. And what you see is that at the higher layer, so this is the layer number, at the higher layers, that injected noise gets attenuated very much. So it started off being the same norm as the vector being computed at the layer, and it quickly got down to being 20%, 10% of the vector computed at the higher layers. So what you find is that the deep net rejects the noise injected at the previous layers. And this is also related to some other noise stability phenomena in some experimental paper at ICLR that was independent. Okay, so now you see that the deep net is somehow very stable to noise injection. And this may remind you of noise-stable computation. So for instance, von Neumann, who was at Princeton and the Institute for Advanced Study, where I'm now, he was very interested in this because, of course, his logical components were vacuum tubes, which failed all the time. And Claude Shannon, in his essay about von Neumann, says that one of his main contributions was reliable machines. And he points out that in human and animal brains, we have neurons which seem to be very unreliable components, and nevertheless, you get a very reliable system out of it. And he suggests that it's done by communication theory or error-correcting codes, okay, which is what von Neumann did. But wait, in deep nets, there's no error-correcting codes, right? So what's going on in deep nets? So let me tell you the noise stability notion, where this noise stability may arise in a deep net, okay? So let's consider one layer, no nonlinearities, fully connected layer. So that's just a matrix transformation. You input some vector x in the layer, and out comes m times x, where m is the matrix of the layer. Noise stability says that if I input, instead of x, x plus eta, where eta is a Gaussian vector, then out comes m times x plus eta, right? And this Gaussian noise had very small effect on m of x. So what that means in percentage terms is that the ratio of mx over x is much more than m eta over the norm of eta. Right? So that's saying that the network, or this layer, passes the signal x much more effectively than it passes noise, which makes sense, right? The whole point of learning is to lock into the signal, right, and reject everything else. But mathematically, what does this mean? Well, what does this imply? So remember the singular values. So this is upper bounded by the top singular value of the matrix M. And what's the right-hand side? Well, Gaussian noise distributes itself evenly in all directions. So it distributes itself evenly in all singular directions. And so a simple calculation shows that this ratio is related to the L2 norm of the singular values. Okay, so largest singular value and the L2 norm of the singular values. So what that suggests, this inequality, is that the singular values are concentrated. And indeed, here's a filter in layer 10 of VGG19, and you see that the singular values are very concentrated. So these are large singular values, and most of them, thousands of them, are very close to 0. Notice that they are close to 0, but they are not 0, okay? So there are 5,000 of them, so they may still contribute a lot to the norm, but there are very few large singular values. Okay, so this is called the layer quotient, okay? This is in our theory, this ratio. In theory, it's also sometimes called stable rank, which is a continuous relaxation of rank. If you didn't understand that, don't worry about it. There's some parameter layer quotient for the layer. And so now what our method does is compression based on this. So now a naive compression for such matrices which have a concentration of singular values is to just discard the lower order singular values. Okay, that's not a good idea in this case. Okay, so instead what we do is some other kind of compression, and at the end what you have is this the number of parameters in this matrix go down a lot, and the training error hasn't changed. And so now this smaller network has the same training error, very small number of parameters than the number of data points, and then this should generalize. So that's the theory. And just as an aside, this is again has to do with the order of the sampling and so on that I mentioned earlier. The theory works if the compression method is allowed to use any number of new random bits, provided they don't depend on the data. Okay, now of course, many of you know that deep nets are compressible, and in fact, that's how they put them on mobile phones and mobile devices these days. But those are more complicated compression methods, and we'll see that this one is very simple, and it has this property. Okay, so here's a proof sketch. So you do this compression of each layer. So you take a layer, compress it, and this compression is going to be randomized in such a way that the errors introduced by the compression, right, because you're changing the layer, is Gaussian-like. And specifically, the compression method is some linear algebraic method where you take k random sign matrices. It's like random linear projection, M1 through Mk, and you take the projection of the matrix, layer matrix, onto these. And there's some extension to convolutional nets as well. So the quantitative bound is something like this. I only define layer cushion, but there's other things, activation, contraction, interlayer cushion, which are then defined, and that's the theory. Okay, so you can measure those on the net, so that's the postmortem analysis, and that gives you an upper bound on the capacity of such nets. So as I said, the checks of such theories are firstly the correlation check, qualitative, and indeed you see that the layer cushion in this case is much higher for a well-trained net than a net trained on corrupted data. And similarly, the plot like this, during training, as generalization error improves, the bound improves. So you know, it's some kind of a theory, but the concluding thoughts, and it gives the best quantitative bounds so far. But the concluding thoughts I have is that although there's still some progress, but the final story is still very much to be written. I don't ultimately know why trained nets are noise stable. You know, yeah, there's noise in gradient descent, but I think there's something more going on. Quantitative bounds are too weak to explain why net with 20 million parameters generalized with 50,000 training data points. As we saw, the current bounds are not so good. And I think what we need is some argument that involves more properties of training algorithm and or data distribution, which we haven't done so far, really. For example, there's this new paper of Gunasekar et al., which tries to argue this, quantify this old notion that gradient descent has an implicit bias towards simpler models or low-capacity models, and it does it in some simple settings. So I think work like that would be very interesting, but you know, with realistic neural nets, not simple settings. So I'm at the halfway point, intermission for 10 minutes. In the next half, we'll talk about the role of depth. We'll talk about theory for unsupervised learning, GANs and text embeddings. And then I'll conclude after that. And so we have a 10-minute break. Please feel free to stretch your legs or ask questions. I'll be here.
Any place you want for lunch? Or? I didn't know how bad it was.
begins. Begin war. Saga begins. Begin war. The saga begins. Begin war.
Intermission. So role of depth. The whole point of deep learning is that there's depth. And we'd like to study that theoretically. And of course, the ultimate hope, as in everything else, is that theory will someday inform what architectures are best for a given task. But currently, we're very far from that. So there's an old question, role of depth, right? Going back to the 50s, as I alluded to, right? Days of perceptron and so on. What's the role of depth? And the ideal result would be to exhibit natural learning problems which cannot be done using depth D, but can be done with depth D plus 1, let's say. So those kinds of questions are very difficult and already. And what makes, in this case, even more difficult is that I insist that you should talk about natural learning problems. And as I indicated earlier, there's no mathematical formulation of a natural learning problem, right? Like dog versus cat pictures. What's a mathematical formalization? So that's not within the reach of theory, but Eldon and Shamir and Talgarsky have recently proved such results for less natural problems. So it's more like for some approximation theory or mathematical approximation kind of setting. And the idea in these new proofs, and there are some follow-up papers, is to characterize the maximum number of oscillations in a function computed by depth D of some size, so oscillation in high dimensions. And then you show mathematically that depth D plus 1 can compute functions with way more oscillations. Somehow adding even one more layer can introduce a lot more oscillations. So that's roughly the idea. Now, as you can see, this setting is very much a mathematical setting, studying classes of functions and so on. It's not clear what it has to do with natural learning. So now, which leads to the question, does more depth help or hurt in deep learning? And of course, the masses of people at this conference shows that it helps a lot, but mathematically, what's going on? And the pros of more depth is, of course, you have more expressiveness, as we just saw. But the cons, traditionally, was that the optimization is way more difficult, and as people realized even in the 1950s. And, for instance, there's a vanishing exploding gradients with higher depths, unless if you use some special architecture like ResNets, which are invented recently. So let me tell you a new result of ours, which I find kind of cute, which is counterintuitive. It shows, counterintuitive for theory, okay? Not, ResNet shows that, yes, sometimes increasing depth can help. But what this shows, even theoretically, is that increasing depth can sometimes accelerate the optimization. Okay? Now, accelerate is in quotes for two reasons. So accelerate, there's a everyday notion that it can make the computation faster. And then there's a technical notion of acceleration as in Nesterov acceleration, okay, the one that's used in Atom. So, so it's also related to that. And the other thing to note is that it's even for classic convex problems you can have this effect. So let me give you the example for classic convex problem. Okay, so LSUP regression. Okay, regression, the simplest learning problem. So you're given data x's. So x is data, y is a label, and you're trying to find a vector w, so that x transpose w, the inner product, is approximating y, and you're measuring it according to the Pth norm. So, so of course the most common is p equals 2, and the effect I'm going to describe does not happen for p equals 2, only for p bigger than 2, okay, even mathematically. All right, but still it's a completely classic convex problem, right, the simplest machine learning problem. So why mess with a simple problem like that? Well, we're going to replace this simple convex problem with depth to linear circuit. By that I mean, I'm going to replace a vector w in this learning problem by a vector w1 multiplied by a scalar w2. So I've overparameterized by 1. Okay? D-dimensional vector times a scalar. So just one additional parameter. So now that's our new objective. Instead of w, w1 times w2. Now you look at it and you say, wait, this doesn't do anything. Every vector can be written as a vector times a scalar, and vice versa. It's the same problem. Yes, that is the point. The overparameterization does not change the expressivity at all. So anything you do here has an analog here and vice versa. However, what may change is the path that gradient descent may take, because the landscape here could be very different. So now with some simple math, you can show that gradient descent now amounts to an update something like this. Wt plus 1 is approximately Wt minus this stuff, which is the previous gradient times some coefficients, and all the other previous gradients. And now for those of you who play with optimization or know a little bit about Atom and so on, what it's doing is an adaptive learning rate, implicitly, and some kind of memory of past gradients. Okay? So it's some simple analog of Atom, right, intuitively. Well, fair enough, but does it accelerate? And indeed, we tried on various regression tasks. So this is a UCR regression task. And you see here simple gradient descent, ADA grad and ADA delta, and R version, the overparameterized version. So indeed, it accelerates. And better than some standard ones. So, and it's even true for wall clock time. Okay, it's accelerating. There are similar effects that we observe in nonlinear deep nets, where you observe fully connected layers or matrices or filters by 2 layers. we give some theoretical analysis for multi-layer linear nets. I mentioned earlier that if you're trying to do theory of multi-layer nets, currently we only know it for linear nets, so we do some theoretical analysis there. And we also show that this acceleration effect by overparameterization is not obtainable via any regularizer on the original architecture. So it's really a different kind of effect. Okay, so that was just an aside. That was just a simple example of the role of depth. Okay, you're overparameterizing via greater depth, and it can accelerate. So it was a counterintuitive effect that was hypothesized at some point, and you can now have some theory for it. So now I'll go on to the next part, which is theory for generative models and generative adversarial nets. So this is in the realm of unsupervised learning. So we're changing tacks a little bit. And remember that unsupervised learning, sometimes also called representation learning, although the two are not the same. And the underlying motivation is something called the manifold assumption, that the data has some underlying simple structure called the manifold, so the image has some simple description on this manifold. And the goal is to use a large unlabeled data set to learn this manifold, okay, this mapping from image to its code. So think of the code as a higher level representation. And so the hope is that you can learn this from unlabeled data, and so now you use much less labeled data, okay, once you've learned this higher level code of the image. Now, traditionally, this was modeled as learning the joint probability distribution PXZ, okay, because every image may correspond to multiple codes and vice versa, so you learn it as a joint probability density. Okay, and as I mentioned, the hope is that this high-level representation is a good substitute for image X in the downstream classification tasks. So which brings us to deep generative models, which try to learn this code. And what they're assuming is that the codes, the distribution of codes, the marginal distribution of codes, is like a random vector, so a Gaussian. So the mapping from codes to images is computed by a deep net, and you input some Gaussian vector here, and out pops an image, a real image. So that's the goal of generative modeling. And the usual training objective in the past used to be a log likelihood objective. And so after this, you get this neural net, which is mapping, which is taking inputs from this Gaussian distribution to some complicated distribution of real-life images, okay, with lots of peaks and valleys. And an implicit assumption in all of this is that this mapping from code to images is computable by deep net of a reasonable size. Okay, and you try to learn it by deep learning. Now, generative adversarial nets change this as follows. They get rid of the log likelihood objective. And the reason they do that is because it's been long known that this log likelihood objective favors that the model outputs fuzzy images. Because the log likelihood objective is really aversive to not putting probability on anything, okay? Because it may get this image on future data, which it may have to put a probability on. So it always tries to generate these fuzzy images, which could look like this face could look like many people. Okay, so instead of log likelihood, GANs use the power of discriminative deep learning, which has been very successful, to improve the generative model. And again, I'm sure most of you have seen this, so just a quick reminder of GANs. So there's this generative net down here, which is trying to produce a synthetic distribution, and there's a real distribution of images, and there's a discriminator net, which is being trained to output 1 on real images. So when it's given images from here, it's told you should output a label 1, and when it's given images from synthetic distribution, it's told to output 0. So that's the training objective for the discriminator. And the generator is being trained to just try to output synthetic outputs or these synthetic images that make the discriminator output high values. So that's its training objective. So they have these competing goals, and it can be seen that this is a two-person game where the objective is something like the probability that the discriminator outputs, let me say it again. The expected output of the discriminator on real images minus the expected output of the discriminator on synthetic images. Okay, so the discriminator is trying to make this as large as possible, and the generator is trying to make this as small as possible. By the way, this objective I just wrote down is actually not the original GAN objective, it's the Wasserstein GAN objective. But I find it more intuitive. But what I'm going to talk about does not depend on the details of these objectives. Okay, so what are we trying to do at the end of the training? So we are hoping to train a good generator. And in this two-person game, you can think of it as an equilibrium. So we think that the generator wins if the objective is roughly 0, which means that the discriminator is at the end unable to distinguish between these two distributions, or not distinguish too much, close to 0. And further training of the discriminator doesn't help. Right? So that's an equilibrium. Or an almost equilibrium, because it's only approximately equal to 0. So that's what we hope for. Now, of course, in GAN's training, this is actually very hard to achieve, to get training error close to 0. But let's say that's the goal. But even if you achieve that goal, are you done? Well, what can spoil a GAN's trainer's day is mode collapse. That the distribution that the GANs has learned, the generator has learned, does not have enough diversity. And the typical way this is described or understood is that since the discriminator only learns from a few samples, it may be unable to teach the generator to produce distribution decent with a sufficiently large diversity, right? Because the discriminator hasn't really learned more than say, 1 million real images, so how can it train the generator to produce a large distribution? And there have been many qualitative checks suggested for mode collapse. So now I'm going to tell you a very simple but striking theory, which gives a new insight, that this problem of mode collapse is not so much with the number of training samples per se, but with the size or capacity of the discriminator. Okay? And we already saw that this notion of quantifying discriminator capacity is a thorny one, but for purposes of this rest of this theory, just think of it as a number of parameters. Okay? So here's the theorem. This was a paper in the last ICML. If the discriminator size is n, capacity is n, then there's a generator that generates a distribution that's supported on n log n images, and it still wins against all possible discriminators. And furthermore, tweaking objectives or increasing training set doesn't help. Okay, so the problem is with the size of the discriminator. And of course, always the discriminator is going to be some modest size, right? A few million parameters. So this is not saying that the GANs can't learn new images. It's allowed to learn new images, but it's not needed to win the game to learn a lot of new images. So presumably the real distribution has infinite support, right? Like all possible combinations of scene elements, lighting, angles, etc. It's really infinite support. And so what this result is saying is that small discriminators are inherently incapable of detecting mode collapse. Okay? So I'll give you a sketch. How does this result go? And it uses this epsilon net argument, the D urchin, C urchin. So the idea is the following. You consider a generator that learns to produce n log n random real images, okay? Don't worry about how, right? We're just describing an equilibrium. We're describing an equilibrium, and this is a generator that learns to produce order n log n random real images. So its distribution is supported on these n log n random images. Now you consider all possible discriminators of size n. And it suffices to consider an epsilon net of these. And now you use the concentration bounds to argue that none of them can distinguish D real from this low support distribution. Okay, that's the proof sketch. Okay, so for those of you who know concentration bounds can fill in the details from this. Okay, so what's the practical implication? So I gave this talk at Google, and my colleagues pointed out there that, well, the theory suggests that GAN's training objective is not guaranteed to avoid mode collapse, but that doesn't mean it happens in real-life training. Right? Real-life training has all kinds of things going on, stochastic gradient descent, et cetera, all kinds of other tweaks you can do. And maybe it avoids these bad equilibria. So the bad equilibria predicted by theory. So I said that's a fair criticism. And how do you check the support size of generative distribution? And so now I'm going to describe to you a very, very simple check that I thought of on the way back from Google. And I thought, almost certainly this check is too simplistic. But to my surprise, even that actually worked. Okay, so here's a test. And it's based on the birthday paradox, and it's from a joint paper with Ristreski and Zhang, both students. So the birthday paradox, remember, is the following, that if you put 23 random people in a room, then the chance is at least a half that 2 of them share a birthday. And it's called a paradox, and we use it to wow the undergrads or freshmen in a discrete probability class, because naively you might think that you need 365 people in a room, or 366, to guarantee that 2 of them share a birthday, but actually, probabilistically, it's enough to have 23. And what's 23? It's really the square root of the number of possible birthdays. So in general, if a distribution is supported on n images, then there's a good chance that a sample of size square root n has a duplicate image. So birthday paradox test is, it flips that. If you take a sample of size S from a distribution, and you already see near duplicate images with good probability, then the distribution, you must infer that the distribution only has S square distinct images. Now there's some asterisk here, some mathematical fine-tuning, but that's the sense. So now how do you implement this birthday paradox test? You're going to draw a sample of size S, and now you're going to use some heuristic method to flag possible near duplicates. So because S is going to be 500 or 1,000, I love my students, but I wouldn't want them to sit for a day and comb through thousands of images. So you use a heuristic method to flag possible near duplicates, and out of a sample of size 500, you may get 10 suspected near duplicates, and now the human will verify near duplicates. And of course, there's some judgment required in saying whether 2 images are near duplicates, because they're not going to be duplicates at the pixel level, okay? They just look like the same scene. And so here are the estimated support sizes from well-known GANs. So this is on Celeb A, the celebrity Facebook data set. And DC GAN, so these were GANs 2017 and earlier. So DC GAN, in 500 samples, you're quite likely to find duplicates, and these are some of the duplicates, so which suggests a support size of 250K, which is good, but it's not, as much as the diversity of human faces. And Bygan and Ali had a support size of about 1 million. There are similar results on CFAR10, and I've seen this year much better GANs, which are doing probably better. They're also using bigger discriminators. The tests also show that the theory that it depends on discriminator size actually holds for these data sets. But these days, this year, there are bigger GANs and they're doing better, but I think there's still evidence of mode collapse in there. Okay, so that's the a simple application to GANs that we had. So you can come in with a very simple theory and come up with some original insights. So in this part, I'll just want to finish by just making a plug that we need to rethink unsupervised learning. So this is a plug for both theorists and practitioners. Because as I described the motivation here, and that people think of it as you're learning this density, the joint density. And the possible hole in this theory that I've been unable to resolve is the following, that if you're going to use this code as a good substitute for the image in downstream classification, then this density Pxz needs to be learned to very high numerical accuracy. Okay, because you're going to use this code Z in some downstream task, right? And so it seems like you need to, and you don't know what the task is. And so it seems like you need to really learn the code Z to very high accuracy. And it's quite unlikely that you have distribution learners in high dimensions that really, can achieve that kind of high numerical accuracy. So it doesn't mean that unsupervised learning can't happen, but just that the usual story is a little bit off. And I'd love to have a better story. And this is, there's some speculation in my blog, offconvex.org. Okay, so the food for thought in this section is that maximizing log likelihood, it may lead to a little usable insight into the data, not be good enough for downstream classification tasks. And how do you define the utility of unsupervised learning in general, or say of GANs, okay? And so, yeah, we should think about, for theory, also, this is a great question, think about unsupervised learning via some utility approach, maybe formalize what downstream tasks we're interested in, and what info do they need about X, okay? So these sounds like vague, mealy stuff, right? Okay, so let's go on to the next section, which is an illustration of these principles. Deep learning-free text embeddings. Okay, so we were thinking along these lines, mulling over this, and came up with something interesting. So what do I mean by deep learning free? So as you all know, that these days the gestalt is that for any task you try to, as much as possible, have a black box end-to-end model, right? You stack together models if need be, and so that it's end-to-end differentiable. You should be able to propagate the gradient, use backprop, right? Backprop is your friend. And of course, maybe clearly there's a lot of power in that. But at least in this setting, this particular setting, text embeddings, I'll show you that artisanal products, handcrafted with love and care, can do almost as well. So what is this? What is text embedding? So think about sentences that humans find quite similar. Let's say, a lion rules the jungle, or the tiger hunts into this forest. Humans find these very similar. But notice that they have no words in common, and so you want to capture similarity and other properties of pieces of text, right? So that's the goal of text embeddings. They capture the essence of text, more than just the word information. So it's some high-level description of this text. And of course, the paradigm is to train an embedding method, a language model, for instance, which is learned on a text corpus in an unsupervised fashion. And this embedding method, this language model also gives you a way to embed, because the language model can sweep a text, and whatever it concludes the text is about, its internal representation, is the embedding. Okay, so that's the current paradigm, and you can get a vector representation from the text. And now this vector representation is your code that you use in downstream classification tasks. Okay. So the obvious inspiration in this is word embeddings, of course, like word2vec and glove, which do this superbly for words. And then the usual method for text embeddings is some form of recurrent neural nets, LSTMs, etc. Although lately they've been replaced by convolutional nets, which seem to do it slightly better. And these are some of the papers. There's a lot of work here, obviously. Okay. Now, what can we do? So remember the Benrecht linearization principle. Before committing to deep model, figure out what the linear methods can do, right? Find the limits of the linear methods. Now, somehow I've seen Ben give these talks, and that was my takeaway lesson from his philosophy. But I exchanged email with him and showed him this slide. He said, nah, that's not really my philosophy. My philosophy is something different. So you should go to his tutorial later this afternoon to learn his philosophy. So I'll just call it the linearization principle. His philosophy is somewhat different. Okay, so, all right, so linear embedding. So there's a cottage industry of text embeddings that are linear, and they do okay for small sentences, but maybe not so much for paragraphs. So the simplest is a sum of word embeddings of the constituent words. Okay, and if you look at the word-to-vec training objective, it's using the sum of the neighboring words as sort of a substitute for the context of a word. So that's the motivation, and it does sort of okay. Then there's a paper, a very nice paper, Weeding et al., which uses a weighted sum. And what weights do you assign to the words? Well, you learn via some fit-to-paraphrase data set. So you take a large data set which tells you these pairs of sentences are similar, these are not similar, and using that you train some weights. So and then there's a paper of ours from last year which is a SIF model, smooth inverse frequency weights, which is the weighted sum, which is completely unsupervised, okay, handcrafted. And it also uses a denoising using the top singular vector, which I won't describe now. But the bottom line is it's linear algebra, okay, linear algebra. So word embeddings plus linear algebra. And it's all handcrafted. So on similarity and entailment tasks, actually it's a champion, okay? So I would love to know if LSTMs out there can even match this. Maybe now they can, but last year they couldn't, but maybe somebody's done better, although I saw a recent implementation somebody did, and they tested various techniques, and this is still the best. So on sentence similarity and entailment tasks, the skip thought is on the left, which is a very well-regarded LSTM method, and even average of word vectors does quite a bit better, and weighted combinations do much better, and our best unsupervised is actually even better, and then if you combine with the Weeding et al. Technique of the semi-supervised, you train a little bit with the paraphrase data set, then actually you get really state-of-the-art performance. Okay. By the way, there's some theory behind the SIF embedding, but you should see the original paper. Today I'll talk about a slightly different theory related to what I was saying earlier. And this came about from thinking about the following. So obviously, the downstream classification task should use a simple classifier, right? That's the whole point of learning a representation, that after you learn the representation, the true structure of the data, now it's trivial to do, or very trivial to do classification, right? So it should be something simple like linear. So then you think about, well, it's analogous to what I was saying earlier. The downstream task is not known ahead of time, so maybe the embedding must capture all or most of the information in the text, right? So for instance, bag of words information, right? Because you don't know the downstream task, right? And it's a completely unsupervised method. So we try to test that hypothesis. So recall the sum of words embeddings, right? You can do it with the other linear embeddings as well. So sum of words embedding. What is that linear algebraically? It's just matrix vector product, okay, sum of words. So what's a matrix? The matrix is the matrix of word embeddings. The column corresponding, so the number of columns is the number of words in your dictionary, let's say 100,000. And in the column corresponding to word W, you have the word embedding for word W, VW. And now when you take the sum of word vectors, what you're doing is multiplying this matrix by the bag of word vector, which is just the sparse vector, which has a 1 in corresponding to all the coordinates, a 1 in all the coordinates corresponding to the words that are in the document. So that's a bag of word vector. So if you do A times X, you're just summing up the word embeddings of the word, of the words in the document. So if that sum of words embedding is doing reasonably well, and as we saw, the weighted ones do much better, maybe you can recover the bag of words information from this embedding, right? Okay. Well, this is the famous field of compressed sensing or sparse recovery, which is very well known in theory, where you're given for some matrix A, the product A times X, where X is a sparse vector. And it's a sparse vector because it has 100,000 coordinates, and it's a vector for a short paragraph, say 100 words. So X is sparse, you're given A times X, and you're trying to recover X. So that's a famous field of compressed sensing. And this compressed sensing is doable according to this theory if A satisfies RIP, random, incoherence, various properties, basically saying if A is a random matrix, okay, intuitively. Now, it turns out, yeah, if you do it with random matrices, random word vectors, sure, you can recover very well, and that's even predicted by the theory. But of course, word embeddings are not random. They are trained according to an algorithm. So we said, okay, the trained word embeddings don't follow the theory, but let's see if you can recover the words. So we use the canonical sparse recovery algorithm, basis pursuit, and which is you're trying to find X, the bag of word vector, and you're minimizing its L1 norm, right, the number of coordinates that are non-zero, but the relaxation of that, and such that A times X, the vector you're finding X, A times X should be the embedding you're given, right, the sum of words embedding. So that's a recovery algorithm. And to our surprise, we find that even with when you're using trained word vectors, right, GLOVE, you recover the documents. This is from some classification data set, SST, and you recover it better than with random word vectors. Okay, so you recover it better than the theory of compressed sensing would suggest. Okay, so this is F1 recovery for bag of words vector. And the orange graph is for Rademacher, which is random vectors. So this is kind of surprising, right, that word vectors actually work better for sparse recovery of text. It's only for real text, by the way, okay? So real text has some structure, linguistic structure or whatever, semantic structure, and then actually this algorithm works better than sparse recovery theory would suggest. Okay, so these linear embeddings are preserving a lot of information. But now you think, okay, wait, but remember the utility question, right? Just because you can recover the original words from the embedding doesn't mean they have good utility, right? Because the utility is they have to do well when you do classification in the downstream task. Right? That's the utility we are interested in, not compressing or recovering, right? Well, then there's a simple result which we sort of rediscovered and then found that it was proved in Caldebank et al. It shows that linear classification on compressed vector AX under these compressed sensing conditions is essentially as good as doing the classification on X. Okay, so therefore it's not surprising that these linear embeddings work well in the downstream task, and in fact, they should probably do so under some compressed sensing type conditions. Okay, so another way to say it is, if the word vectors were random, right, which is what the compressed sensing theory says, right, that corresponds to an LSTM with a random initialization of word vectors. So an LSTM with random word vectors should be able to produce really good text embeddings. That's what this is saying. Okay? And it's interesting that in the LSTM work, people empirically compare to the bag of words information or bag of n-gram information. And actually, they don't sometimes do as well as bag of n-grams. But actually, the theory says you should. So it's actually interesting. Just by designing the text embedding, actually, you can probably do better than many LSTMs that are out there right now, okay, on some tasks. All right, so these are the powerful linear embeddings that follow that train of thought. And this actually drew inspiration. Again, we were rediscovering things, and we discovered there were some related ideas in the theory of distributed representations. Okay, this is neural theory, like for neural brain, and people study distributed representations, and there are these classic papers. So distributed co-occurrence embeddings, okay, so instead of bag of words vector, it's actually going to do a compressed sensing of n-gram information, okay? Bigram is word pairs, trigram is word triples. So we are even going to do a compression of that. Again, linear compression, and you define an embedding for bigrams, trigrams, etc., using entry-wise product, and you use that in the linear embedding. That's it. Okay, so that already does pretty well, as we'll see in the next slide. And then in a recent paper, we've improved it using what we call a la carte sentence embedding, which says, actually that compressed sensing isn't so great. You should actually learn, right? That was the message of that compressed sensing slide, right? The compressed sensing vectors are actually not so good. So actually we learn the correct embeddings for n-grams using linear regression. As you can see, my mathematical development is stuck at linear algebra. Using linear regression, you induce some new embeddings, and those turn out to be much better, or a fair bit better. So here's some comparison, okay? So the money slide. So So on the top is bag of n-gram vectors, okay? And this is a suite of text classification tasks downstream. And bag of n-grams has some performance. On the bottom are LSTM-based methods. All of them are pre-2017, except the last one, which is 2018. So we're only going to, we do better than the 2017 and earlier LSTM methods. And you can see that the a la carte embedding on many tasks beats the like skip thoughts and the other methods. Okay, so here's a handcrafted embedding, right, in this day and age, which actually beats very powerful deep learning methods on downstream tasks. Now, possibly, and many people suggest this, what this means is that these classification tasks are too easy and they're not really relying too much on a good language, understanding of language structure. Very likely true. And an open problem for theorists is, look at this embeddings and try to come up with handcrafted analogs of attention and character level LSTMs. Okay, that's an open problem. So before I finish with this linearization principle in RL, I also want to talk about or mention, this work that I think Ben Recht will talk about later today, where they show that in simple linear models in reinforcement learning can be the state-of-the-art deep RL on some standard RL tasks. So that's a very interesting example of the linearization principle as well. So wrapping up, so what to work on? So these are suggestions for theorists. So here's some things that I would love to understand more myself. So use insights from physics and partial differential equations. There's a lot of ideas like calculus of variations, which I wish I had learned more about in my undergrad days. And I think those are very relevant, and there are people working on them now. Look at unsupervised learning, if that wasn't clear so far. That's that I find very fascinating. And yes, everything is NP-hard and new, but that's how theory will grow. As Jan says, the revolution will not be supervised. Theory for deep reinforcement learning. Currently, there's very little, and that's and it seems everything there is not just NP-hard, but maybe even P-space hard, even harder. So it's very tricky to do theory there, but I think it's worthwhile. And probably one has to start, as Ben Recht is doing, with simple linear models or something like that, and do the theory there. And going beyond 3, it's something I'm very interested in. Design interesting models for interactive learning of languages, skills, etc. And I think here, theory can really come up with some crucial insight, because it seems that even the applied work here seems to be missing some basic idea. I mean, the applied work is not doing anything very complicated here. And the theory, on the other hand, is focused on some very simple settings like linear classifiers and clustering. So it would be very nice to have language learning, like what all of us did, right? At some point we were born and we knew nothing, and from there we went to knowing a complicated language by age 3, and it was all interactive. So, all right, so to conclude, deep learning is a new frontier for theory with many new avenues. The best theory will emerge from interacting and engaging with real data and real deep net training. So maybe this is more a message for theorists, because in the past, for SVMs and other convex models, one need not need to do the experiments as much. But I think today, remember, we are in sort of this postmodern mode where we're looking at what's going on empirically to even begin to come up with a guess for what the theory might be. So I think that's very important, and we theorists should have our students engage with real data and real deep net training. And finally, I'm very optimistic that deep learning methods can be understood and possibly simplified and maybe made more powerful by this understanding. And as is usual in these things, one recalls Hilbert a century ago saying, in mathematics, there's no ignorabimus. We will know. Thank you very much. And I'll take questions. Yeah, so we have, I believe, even 15, 20 minutes, so I'm happy to answer lots of questions.
And there are 2 microphones.
2 microphones there,
on
yeah.
each side.
Thank you.
Yeah, let's thank Sanji for a wonderful talk again, I guess. I guess they already did.
Is there a question? Yeah, go ahead. Is it on?
Yes. So in the, very nice talk, by the way. Thank you. So in the section on depth that you mentioned, some of the results that increasing depth led to greater function complexity. How does that jive with the classic result that one hidden layer can approximate any?
I think I mentioned that on the slide, but I forgot to emphasize it.
Yeah.
That we're talking about nets of a certain size.
I see.
So that classic result that a single layer net can express everything requires gigantic nets.
Okay. Thank you.
Next question.
Hey, thanks for the talk. I like how it was very math-geared, so I figured I'd ask you a math-geared question.
Okay.
So have you ever seen any of these tools being used for predicting low-dimensional dynamical systems specifically? I saw you have some ideas about PDEs, and I know there's the other way around, using dynamics to predict networks, but have you seen anything that's the other way around?
So you're using networks to predict dynamics. Yeah. I mean, almost any task out there, I think people are applying deep nets to, and I've seen things like that. Empirical work, yeah. Like there was this thing that got a lot of press that, there's chaotic systems, right? And they were even training deep nets to predict the chaotic systems, which they can do given enough capacity.
Right. And so you could train, you could technically ingest images of fractals and then, figure out math patterns behind, what the similarities between the fractal structures are. Have you ever seen anything like that, perchance?
No, I haven't done anything like that, yeah.
Okay, thank you very much.
Is there a question there or no? Yeah.
Again, thank you very much for the talk. Similar to the previous question about how expressivity of networks scales with depth, I wondered if you could comment on, so the argument goes that the expressivity of the function increases quicker with depth than it does with width.
That's right.
So we get more expressive functions if we're deeper.
Yeah.
But then the generalization stuff says that as we get extra capacity, we're going to overfit more.
That's
so how
right.
do these two things jive?
Right. That was exactly the tension I was raising in those slides. That's a classical statistical theory that more capacity leads to overfitting, and somehow it doesn't seem to happen in deep learning.
I guess what I'm asking is, if we're not exploiting that extra capacity, then why is that the thing that explains why they work better?
You mean explains as in theoretically explain?
Yeah.
Well, that's what the ultimate theory would do, yeah. I'm not sure I understood your question.
Sorry. Maybe I'm not being clear.
Uh-huh.
I guess the question is that the generalization results seem to suggest that the extra capacity is not being used because we're not overfitting, and yet the depth, sort of the explanation for why depth helps, is because it increases expressivity.
As I indicated in another part of the talk, I'm not sure if the depth is helping only because of expressivity. We saw that adding depth can actually help the optimization as well. So, and that's also conjectured for ResNets, that somehow the ResNets improve the optimization. So it's sort of all complicated. There's expressivity, optimization speed, and generalization. They're all sort of in there, and we have to tease them all apart.
Thank you.
Yeah.
I wonder if you know any work that has some theory to understand the robustness of deep learning, like the adversary machine learning topic essentially says that deepness is really not robust to perturbations. Are there any theory behind it? In principle, of course, it need not be robust, right? Because even the generalization bound just says
that you should generalize only on the training, on the test data, right? Like from the same distribution. So there's no reason, I mean, it's not surprising that adversarial examples exist. Maybe what's surprising is, things like how easy it is to find adversarial examples, right? But yeah, so there's no theory explaining that. The theories that people are trying to do are more in the reverse direction. They're trying to change the training in some way so that you're immune to adversarial example. And there's been some successes with depth 2 and so on, but it's still very preliminary.
Okay, thanks.
Hi, thanks for the talk. Did you manage to leverage some of the ideas in the proofs to real algorithms, better optimization of neural networks? Or did it give you new ideas?
Yeah, so, it turns out that this field is so vast, right, empirically, that almost any idea you try, somebody has tried, right? So, like the Gaussian noise injection experiment, right? It suggests that while training, you should try to inject Gaussian noise. So people have tried that, and it helps, but dropout seems to do better. The overparameterization by depth, it suggests that, you should use low rank, replace all matrices that are, complete, like in filters and so on, with low rank matrices, and that helps. So it's very hard to come up with radically new ideas that people haven't tried. Yeah.
Okay.
One keeps trying, but yeah.
Thanks.
Hi, thanks for the talk. We have seen a couple of papers relating renormalization theory with deep networks. Any thought about that?
Yeah, so those are among the physics ideas that I mentioned that, I, in principle, would love to understand more and develop more, and sometimes wish I had taken the relevant courses in college. But as far as I know, I've tried to make sense of some of it, and it's like a fair bit of physics work, sort of semi-theorems, right? And sometimes some of those theorems actually lead to the wrong conclusion even, the semi-theorems. So yeah, I think it's worth exploring, but with those caveats.
Hi, thank you for the talk. I'm not sure if I missed this part, but is there any theoretical understanding why adding second-order gradients to backprop doesn't work very well in practice? Yeah, so there's some subsequent work which I didn't mention. Maybe I'll put it on my website. By the way, there's a website for the tutorial where I'm putting a bibliography. And that suggests that actually the first-order method is basically incorporating most of that information. So they're saying, it's Hessian-free second order, something like that. So I haven't read the paper, even though one of the authors is my student. But yeah, so that's an explanation, that the first order methods with noise are already incorporating that information. Okay, thank you.
Thanks for the excellent tutorial. So I was wondering, you mentioned one interesting direction is to do theory for deep reinforcement learning. So do you have any feasible directions or suggestions for young researchers on this topic?
Yes, so I think the model that Ben Recht has been really pushing, which is this linear models, right, the LQR and so on. Those are very interesting. His group has a few results. The Princeton folks have some initial results. Yeah.
Yeah, but regarding the deep RL.
Yeah, so that's one has to start with the simplest things, right? We don't even have something for deep discriminative learning, right? Except for depth 2. And for deeper, we only have for linear nets. So yeah, we don't even have theory for deep discriminative learning, right? Really.
Thanks.
Hello. Hi. Thanks for the talk. So before you mentioned that it's surprisingly easy to find the adversarial examples. I was wondering if you have any thoughts on if that's because the networks are open loop as opposed to closed loop, like you have in control systems, where you can design systems to be stable and automatically have this kind of attractor basins?
Yeah, so I think that's the idea of adversarial training, right? That you incorporate the generative process for adversarial examples into the training and make it resistant. Did I answer your question? That's kind of like a closed loop.
Yeah, I was thinking more making the the loop in the network itself.
In the network itself. Yeah, I don't know if anybody's done that. Yeah.
Hi, I found your example of adding the single parameter, the scaling factor, really interesting. Is there any theory in how this might help with generalization, things like transfer learning?
Generalization. All our overparameterizations are not changing the expressivity. So I think they only help the optimization. So in fact, that's why we studied in those settings, where expressivity is not changed and still optimization changes. So I think so I think you would have to change the class of models being changed, right? By overparameterization or somehow.
Yeah.
Yeah.
Interesting. Thank you.
Hi, you mentioned the work on using the birthday paradox to estimate the effective support size. So this might be answered in the paper, but have you applied it to the real data set? Have you tried it on the real data set? What is the effective support of that? And you could also ask the same question of like the actual underlying data, such as human faces. Yeah.
Right, you could. But notice that the finding was that it's not just that you find the same people, but actually essentially the same pose.
Same
and
pose, yeah.
Right.
So it has to be, yeah.
So I don't think the faces data set has that low. You don't find such close matches.
Yes, you would expect it to match the. So you actually have 200,000 then.
Yeah.
No.
No. So the correct analogy is, let's say, so think about the birthday paradox in your own life, right? So most of us know a few thousand people, right? You add up all the people we've known over our lifetime. We never see doppelgangers, right? People who are so similar that if they're standing in front of you, you say they're the same person. So except for twins, right? Yeah. So it's kind of unusual to find doppelgangers, like almost the same pose and everything, with sample size of 500.
So I guess arguably the thought would be that once you take a low resolution image with similar lighting of say people who are celebrities, so they're selected for a particular look, you might start finding more similarity.
I agree. But so let me mention, like progressive GAN is like the latest, greatest GAN. It produces lovely pictures. And I was just at a talk at CVPR. I was giving some of this at CVPR. And Alyosha Orfros spoke after me, and he said, yes, he thinks GANs do memorize, but he loves it for that. And he showed examples from progressive GANs, that you navigate in the Z space, and not faces. I mean, faces are a simple structure, but real life scenes, and basically it just goes from one memorized scene to the other. That was his conclusion. Yeah. So, for whatever it's worth, at least one expert in vision seems to think this is true.
Yeah. Okay. Thank you.
Thank you for the great talk. I'm wondering, you mentioned a couple of times that the overparameterization doesn't change the expressivity.
Oh, only for that experiment. Yeah.
But even in that experiment, if you have something like weight decay, L2 regularization, then it does affect it. And,
this was
and
without.
I'm wondering on your thoughts on how it would affect it.
So we keep all of that constant. So the only thing we change is the overparameterization, none of the others. But
right, but you have another weight that is now being regularized.
Yeah, but so I forget the details. I'll have to think again. But yeah, we control for all of that, if that's your question.
But you wouldn't think that it affects generalization at all?
This experiment was only about optimization, not generalization. Yeah.
Right, thank you.
Thanks again. So a quick question about the first part of your talk, which ended with showing that the matrices implicit in those linearized neural networks are essentially all low rank.
Not just linearized. VGG19. That's a real life net with nonlinearities.
Okay.
Great. I only analyzed it for one layer. That's why it was linear. Yeah.
Okay, perfect. But how much is this dependent on initialization and what SGD can do to escape, say, like if you initialize it with what looks like a low rank matrix, can it ever find anything else? And vice versa, if you initialize them, they would end up being a high rank matrix.
Okay, so what is true is that the difference between the final matrix and the initial matrix is also low rank.
Okay.
Yeah. So basically, it sort of grows in some directions, And that's really the low rank structure.
Thanks.
Thanks for the talk. So you mentioned a method where you can compress a neural net by projecting it onto k-binary vectors. So can you use this to actually sort of compress the network so that it would fit on a sort of a phone? And have you compared that with sort of other methods that actually learn to compress?
Okay, so yeah, that's a great question, you know, and it does compress a bit, right? But the reason for our linear algebraic method is because we need it in the proof. You know, we have to analyze what happens to the errors. If you use some arbitrary compression, you know, zero out things here and there, looking at, you know, it's not clear what the errors are, right, and how they affect the subsequent layers. That's why we need the linear algebraic. You know, it's basically matrix sketching. So we need it for the theory. Almost certainly, you know, all those crazy things, I mean, there are like dozens of methods for compressing. Almost certainly you put the whole kitchen sink together and you'll do better. So yeah, so that part of, you know, the linear algebraic compression was more for the theory, I think. But one should try in practice.
Hi, thank you for your talk. I really enjoyed it. My question is about the folklore experiment that you mentioned in the first half of the talk, where it is difficult to retrain a new network to mimic an old network with the same amount of nodes. But if you increase those nodes, it becomes easier. This seems to be at odds with like the model distillation work, where you take this very large network and teach a smaller network to mimic its behavior, and that does actually work. So I'm wondering if you have any thoughts on how these two things can be consolidated, or those two experimental results.
Yeah, so it doesn't rule out that, right? Because in model distillation, if I understand right, it always uses a lot more data, right? You sort of take more data and pass it through the net. And
I see.
so I think that's the explanation there. That there was a small net all along, which could have been learned, but because you didn't have enough data, you couldn't learn it. So yeah, so I think that's probably the explanation.
Okay, thank you.
Yeah, in that experiment, you can use as much data as you like, because you have the net before you input, output as much data as you like. One more question.
I have a quick question.
Yeah.
Yeah,
Oh, sorry.
so it's regarding the compression. So you said when we are trying to do low rank decomposition to compress networks, so why do you think like PCAs won't work? Like, what is a more principled way to do low rank decomposition of networks?
PCA probably does work, but I don't know how to analyze it.
Yeah, but in your talk you mentioned PCA might not, like principal component decompositions might not be the greatest idea to compress.
Just for theory. You know, as I was saying, in practice, probably all of those dozens of methods for compression probably work, but to actually prove that they work is very difficult. And so that's why we have this linear algebraic compression where the errors are Gaussian-like. So the effect on the subsequent layers is like Gaussian.
Do you know if there is any work on the analyzing the loss surfaces after you do like principal component analysis of the weights?
It's a good question. Yeah, one should study that. I haven't done that.
Okay. Thank you.
Thank you for a great talk. I had a question regarding the estimation of supports of the generator. The images are continuous, right? So how can we define the size of the support in that case?
Right. So it was that's what I'm referred to as near duplicate images. They're not pixel level duplicate, but a human looks at it and says it's the same person with roughly the same pose. So that's the fuzziness. I remember in the theorem I had this asterisk, so that was one of the asterisks. And yeah, I mean, it's just, you don't expect to see in the original data set 2 images in a small sample, which are so close.
So it's based on human's perception, right?
Yeah.
Okay, thanks.
Yeah. And there's subsequent work which tries to do away with the human in those tests, actually.
So I was curious about your thoughts. I guess there's a few observations in optimization for modern neural networks, which is one, that the global optima for training loss isn't necessarily the best generalization. and two, that there's actually in local minima, there's many local minima which have many different weights but seem to have the same generalization error. So I guess it's two observations. I'm curious if there's any theoretical work or thoughts that you have to explain kind of why.
Yeah, so the global optimum probably, won't satisfy the magical properties that we need for like even noise stability, right? So that's probably the explanation, right? The global optimum is too special structure, right? And so that's that. And then the local optima all being roughly the same, I don't really believe that conjecture, that all local optima are equally good. I think the local optima that SGD finds seems to be good. That doesn't mean all are good. And in fact, I think there are some, it's known that that's not true. I'm blanking on what that study was. I'll try to look it up and put it on the website. Oh, one last question, okay.
So you mentioned that learn embedding perform as well as learning something end-to-end for classification tasks, right?
Almost as well, yeah.
So,
as well as the 2017 methods, yeah.
Yep, so is it just for classification tasks, or you can sort of generalize this result to, let's say, regression or learning value function in reinforcement
or translation,
learning?
Machine translation, for instance.
Or let's say you're doing value function approximation using some representation that you learn by.
Oh no, regression, there are some tasks which are regression, yeah. Like some of the sentiment tasks are regression.
Right, okay,
yeah.
Thanks.
But yeah, like language to language kind of mapping, that's probably more difficult. And that's where you need the LSTMs, maybe. But I want to try that even with linear models, actually. Okay, I'll probably stop, yeah. So thank you very much. Anything you want to say, or? Okay. All right, thanks.
Okay.